Hello, I'm Thomas Detlefsen, and I'm a member of the 2021 Carnegie Mellon University Robotics Institute Summer Scholars Program. This summer, I got the fantastic opportunity to work in the Biorobotics Lab with Cheyenne Mondal and Dr. Matthew Travers on the problem of simultaneous localization and mapping, or SLAM, on legged robots. Legged robots are vital for robust applications of mobile robots where wheeled and tracked robots fail. They have distinct ability to navigate new and complex terrains such as woods, industrial sites, and urban environments. This makes them the best choice for exploring new and complex terrain. With this ability, legged robots can be applied to many fields such as industrial inspection, exploration, and search and rescue missions. The field of localization is large, and there are a large variety of SLAM systems that are suited for different purposes. Many general SLAM algorithms are effective in cases such as wheeled or flying robots, but have degraded performance when it comes to legged robots. Even SLAM algorithms specifically designed for legged robots have trouble with effective performance at higher gates. The difficulty in accurate localization occurs because a legged robot performing at high speed in an uneven environment has a rapidly moving body. This degradation in performance is shown below, where SLAM systems are applied to a legged robot moving at 95% of its full speed. The first system is designed for legged robots, hence its lower rate of error, and the other ones are general SLAM systems. In our paper, Joint SLAM on Monocular Cameras for Legged Perception, we present a method for robust SLAM on legged robots using monocular vision. In this work, we represent features as objects moving between multiple cameras on a conveyor belt. The re-identification of objects in another camera is representative of the feature re-identification. We chose this representation to abstract away the details of feature selection in SLAM, as this ability has been demonstrated consistently in many modern SLAM systems. Our method contains 4 stages. First, the objects are recognized by the detection algorithm and bounding boxes are generated around the object. The objects are then classified based on these bounding boxes. Then the bounding boxes and classifications are passed to the tracking module, which generates an ID based on the features and trajectory. This data is then used to inform the next tracking module so that the objects can be re-identified in other frames. While we do not have full results in the form of a fully actualized SLAM system implemented on a legged robot, we do have results from our initial implementation. The first example we have is of our detection and classification modules implemented and tested on a series of objects moving on a conveyor belt. Each of the objects is identified and classified, and an ID is generated for each of them. The ID and class are used to keep track of the number of objects passing by the camera, shown on the left. The confidence from the detection module is shown on the bounding box next to the class. As can be seen, there are some misclassifications by the detection module because it does not use information from previous frames. This is why we chose a RNN, which utilizes information from previous timesets for classification. In this example, the classification confidence is compared with our detection and classification modules, YOLO and CRNN, respectively. The confidence from the detection module is very inconsistent and does not correctly classify the object until a few frames after the object has been seen by the camera. For the classification module, the object is immediately and correctly classified, and the confidence increases consistently as more frames of the object are seen. We intend to continue the development of this method so that it can be fully realized and demonstrated on a legged robot. Our first goal is to integrate all of the modules in real time. The second is to integrate multiple cameras in tandem, and our final goal is to adapt this method to feature selection and tweak it so that it can be deployed on a legged robot. I would like to thank the RISC program managers for providing a fantastic opportunity. I would also like to thank Cheyenne Mondal, Dr. Matthew Travers, and the Biorobotics Lab for helping to guide me in my research. Finally, I would like to thank the National Science Foundation for supporting this research experience for undergraduates. Thank you.